Analysis and discussion. 5 flights and 10 cloud systems were selected for analysis based on a visual evaluation of the records made with the forward and side-looking video cameras on the aircraft. The criteria was that no other clouds could be seen within around 10 kilometers on either side of a cloud line, such that far cloud samples represent ambient aerosols, i.e., lacking any recently processed particles by clouds. We studied the data from flights 7, 9, 12, 13 and 17. The flights were conducted in convective clouds by passing through the clouds at different levels, 1,000, 2,500, 4,200, and 6,000 meters. Moreover, we passed through the cloud base, 300 meters, and at surface level, 30 meters. Cloud processing signatures. Furthermore, during the flights were conducted surveys of the atmosphere's vertical profile. This information is useful because surveys have different locations, but they are associated to the cloud's recorded data. We observed changes in the properties of atmospheric particles and the processes responsible. Also, we recorded environmental and weather conditions in zones which the property changes occur more frequently, comparing both sides of the clouds. The droplets concentration in a cloud is function of the particles number in the atmosphere, so any variation in the amount of particles will affect the cloud microphysics evolution. In marine areas the concentration of particles is about 100 per cubic centimeter. If there is a greater amount of particles is likely to pollution particles are present. The EPIC 2001 research area is located approximately 800 to 1,000 kilometers away from Mexico and Central America, allowing the transport of pollutants from the continent to the area when the prevailing winds are favorable. The opposite situation is also possible in maritime areas away from the coast. Wind patterns during flights 12 and 13 shows weather characteristics of maritime areas. The cloud boundaries are identified by means of videotapes taken from the plane C-130 and the analysis of time series using reference measurements obtained by the FSSB 100. The criterion was to consider the instrument's concentration records greater than or equal to 1 cm-3 obtained within the cloud. In EPIC 2001, we identified 10 cloud systems that met the minimum information necessary for the study. Table 2 shows the location, date and time of each cloud systems. The data correspond to the average information of all transects made to the system. Characteristics of cloud systems selected for the analysis. Flights 9, 12, and 13 were made on days with maritime, Mr. aerosol background and when winds came from the southwest. Higher, Hg, aerosols concentrations correspond to flights 7 and 17 with average concentrations significantly higher than the other 3 flights. Table 2 summarizes the time, location and type of cloud systems. A convective cloud in its formative stage has a rapid vertical development. The ambient air surrounding the cloud incorporates into the cloud, increasing its volume with the vertical expansion. This process is known as entrainment, so its mixing process is more efficient outboard in the cloud with subsaturated air from the environment. The droplets evaporate and particles served as CCN are released back into the atmosphere. The mixing with ambient air and the evaporation of cloud droplets produces a cooling air parcel which generates a negative buoyancy force. This could result in shear zones, as the turbulence caused by this effect helps to mix ambient air with the cloud and evaporate more drops. To define the distance corresponding to the cloud border, we did a time series properties analysis of the particles in the clouds, to evaluate the zone of influence. Shows the changes in properties of the particles in the vicinity of the cloud. The area of influence for the interaction of particles with the cloud covers a distance of approximately 500 meters from the cloud's border. The FSSB 100 drops concentration measurements correspond to the solid line, which marks the cloud's boundary. Each tick mark represents 110 meters at the aircraft's average velocity of 110 meters s1. The dotted lines represent the behavior of the average diameter of particles measured by the FSSB 300, and FSSB 100, and dot. These values denote the limits of the transition region between ambient and cloud air. Diameter measurements show a significant increase of particles up to 500 meters from the cloud's boundary. That determines the representative area to evaluate the mechanisms that modify the properties of particles due to the interaction with the cloud. Medium volume diameters measured by FSSB 300, line, and FSSB 100, line, indicating a cloud boundary. The particle's properties on both sides of the cloud border must be different. The particle's characteristics in the neighboring area of the cloud have a determining effect on the modification of some of their properties. Changes in humidity, altitude and environmental conditions, where the samples are collected, affect the particle's concentration and size. So, in order to compare both sides of the cloud, we analyze data from the cloud's vicinity, 500 meters from the border of the cloud, to obtain average values. Shows the average concentrations of vertical profiles measured by the PAHs, greater than 0.1 microns, on the cloud borders, cases identified by U, D or P. A third profile, corresponding to a far area from the cloud, average 500 to 1,500 meters from the border, dotted line, is used to compare the profiles against those close to the cloud. In conditions with and without pollution, particle profiles measured in the vertical gradient has two patterns. One shows a constant value or a decrease with height. The second shows an increase in concentration up to 2,500 meters and then decreases to lower values than those measured at the base. It is possible to observe cases where the particle concentration profiles are similar to the concentration profile far away from the cloud. This is due to the presence of dilution processes, where particle concentrations in the vicinity of the cloud are lower than in remote areas. When the concentration of particles near the cloud is greater than the environment, it is possible that there is an increase of particle size less than 0.1 into ranges that is not possible to detect. In summary, measures of concentration of particles increased with height, indicating that the smaller particles, less than 0.1 micrometers, at the base of the cloud grow to detectable size ranges for the instrument during transport through the cloud. On the other hand, when the concentrations decrease with height, means a dilution effect. Vertical profiles of particle concentrations measures for the 10 cloud cases. The far cloud profiles, short dashed, and near cloud profiles on each side of the cloud, solid and long dashed lines. Shows concentrations measured with FSSB 100, greater than 2 m, in the vicinity of the cloud, solid and dotted lines, and away from the cloud, dotted line. In the region where there are drops of cloud measurements, we use them to detect giant particles, greater than 1 micron, coming from the ocean. In most cases, the concentration values for particles greater than 1 micron near the cloud have a maximum at 1,000 meters high. It happens perhaps because smaller size particles increase their volume within the cloud. Sometimes it is possible to observe when the particle concentrations decrease with height that there is an increase in the concentrations of larger diameters. The combination of patterns is indicative of changes in particles by mixing and dilution on the total concentration dominated by small particles. Also, a simultaneous increase in the concentrations of particles suggests that there is a change in particle size. The vertical profiles of concentrations measured with the FSSB 100. There are different processes at each side of the cloud and in each level of each cloud's system. We used as reference the processes' signal description and their property. This subjective classification is based on an examination of vertical profiles, shown in figures 4, 5, and 6, and on the shapes of PSDs associated with the near cloud region at each level. The 300 meters passes were only evaluated for evidence of removal by precipitation. Pattern D summarizes the frequency of each category. There were 49 classifications made on Mr. days and 35 during HG days. A classification could not be made in 10% of the Mr. cases and 5% of the HG ones. The largest fraction of the observations was classified as Pattern A, 40% and 60% of Mr. and HG cases, respectively. Pattern C matched only 4% of the Mr. observations and none during HG days. Patterns B and D were equally represented during both Mr. and HG days. Percentages of cloud processing signatures, derived from vertical profiles of particle properties and evaluation of particle size distributions, for the Mr. cases, bottom panel, HG cases, middle, and combined cases. There were no consistent trends with altitude between Mr. and HG days. Particles at 1,000 meters and 2,500 meters altitude were predominantly like Pattern A, in both the Mr. and HG cases. In Mr. cases, there were slightly more Type B than Type A particles at 4,200 meters. In HG cases, the 4,200 meters particles were evenly distributed between patterns A and D. The refractive index was used to estimate the particles' composition at the ends of the clouds. We calculated an average refractive indices at 500 meters from the borders of the cloud. Shows the results. The refractive index profile for the area between 1000 and 1500 m away from the border of the cloud is also shown.